Welcome everybody. Today we're going to start looking and understanding how can I distribute the electrons and the orbitals. So let's start with the first thing, which is how can I fill these electrons of an element in shells. 1s refers to the number of shells. So you're in shell number 1. This s subshell here indicates, or let's say contains only one orbital, which is the square that we can see here. And the maximum capacity of S is 2 electrons. So you will start filling the 2 electrons first. Put in your mind, we're gonna look at this sequence. You notice that once you finish the 1s, you will jump to 2s, and after 2s, you're gonna go to 2p, and from 2p to 3s, etc. We call filling these shells depending on the sequence Ioffe principle. It's called Ioffe principle. So this is the scientist, his name is Ioffe. He said that the electrons start to fill from the lowest energy level in a sequence. So why did S fill first in here? Why do we fill it first? The reason behind, because S is the lowest energy level, since you have 1S in here. The 1S, which is the first shell, is the lowest energy level, and that's why it's filled first. So the lowest is always filled first. Very nice. We notice something in here. If we look at these orbitals, let's go to 2s for example. You notice that the maximum capacity in the orbital is 2 electrons, as we can see. And these 2 electrons is also a principle. And the scientist who said that we have only 2 electrons in one orbital, his name is Pauli. This scientist has a name of Pauli. Okay, his name is Pauli, and he said that the maximum capacity of an atomic orbital is 2 electrons. All right, and the 2 electrons in this case must be in opposite spin. Put in your mind the electrons can spin clockwise or anti-clockwise. So these electrons must spin like this in the opposite directions to decrease the repulsion forces. Okay, and that's why we can occupy them in this place, which is the atomic orbital. Okay, so this is the idea. His name is Pauli. We have 2 electrons. They must be oppositely spinning to each other. The reason behind is to decrease the repulsion forces. All right. But why do we have repulsion? Because you're talking about 2 electrons, and the 2 electrons are identical in their charges. They have negative charge. And that's why we're supposed to find, or let's say, to undergo a repulsion forces. So how the repulsion forces take place for 2 electrons, and they're in the same position like in here. So this is the idea behind that. Right. So the scientist number 1, he said that we can start filling the electrons from 1s and can go to 2s and then 2p, 3s, 3p, 4s, blah, 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 until the end. His name is Ioffe, and his principle is called Ioffe principle. And then we got to the atomic orbitals that contains the maximum capacity of 2 electrons, and these 2 electrons must be in opposite directions to decrease the repulsion forces. Very nice. Okay, let's go to 2p for example. Okay, like the p orbital. We just noticed that the p subshell in here contains 3 orbitals. This is orbital number 1, number 2, number 3, or px, py, and pz. So these atomic orbitals, how can I fill them? Suppose that you have in 2p orbitals, let's say 5 electrons. Okay, how can I fill these 5 electrons? Okay, is it like this? You're gonna fill like 1, 2, 1, 2, and then? Okay, is it the best way for adding these electrons? Or can I say like this and this and this, and then you like this? You'll notice that in this case, we'll have the same results. But the best way is filling the orbitals using this one here. Which means, let's take another one. Let's say 2p4. And this 2p4, you have to distribute the 4 electrons in the p orbitals, as we can see. So if I want to distribute the 4, we can put like this and this. But this is actually, it's not correct. You have to add electrons, fill the shells first before pairing up the others. We fill the 3 and then we have another one. So this is the correct way of filling the electrons. So you have to add one electrons in all of the shells in here and then pair them up. We call this a principle Hans rule, and actually it belongs to a scientist whose name is Hans. And that's why you have to fill the electrons in the shell and then pair them up. Okay, let's go and solve some equations. Let's take different parts. Put in your mind, you have to put in your mind to memorize the order of these shells which are filled first. Okay, I want to take this an example. Let's take random atom, which is P, phosphorus atom. Here is a phosphorus. It contains 15 electrons, so we can say P, 15. How can I fill them? According to the I of Pop principle, we're going to start filling the 1s first since it's the lowest energy level, and we can say 2. The 2 superscription here refers to the number of electrons occupied in S, and then after filling the S, we're going to go to 2s, and actually it occupies 2 electrons too. Very nice. Now we filled 4 electrons out of 15 electrons, and then we got to 2p according to the sequence. And you notice that P contains the maximum capacity of 6 electrons, and then we put 6 electrons in here. Now we fill 10 electrons. How many electrons left? We have 5 electrons. You have to go to the 3s and fill 2 electrons, and now we filled 12, and then we go to 3p. How many electrons we should add? We have to add 3 electrons. What do we conclude from this one? Okay, I need to do here the okay, very nice. Let's come here and see what is the lowest energy level in here. The lowest energy level is 1s. This is the lowest energy level. What is the highest energy level in this case? This is P. This is the highest energy level, right? Because it's the last one which is filled. The highest energy level is the 3p. You have to determine and tell me about the 3 here, which refers to the quantum, principal quantum number, which is the number of shells or the energy level number. So we have to say this is the highest energy level is 3p. The lowest energy level is 1s. Why this 1s here refers, or it's considered as the lowest energy level? Because it's filled first. What about B? Why we consider it as the highest energy level? Because it's filled lastly. Okay. Another thing to put in our mind. Let's take another example of Fe26. So we want to fill these 26 electrons. And according to the I of Pop principle, we start with 1s, okay, and we have 2, and we got 2s, 2, 2p6. We filled 10 electrons for now. And then we got 3s, 2, and then 3p6. Okay, till now, how many electrons were filled? We have 10 electrons and we have 88, so the total is 18 out of 26. How can I add the rest? Yeah, depending on the number of electrons that are filled first. Look at this. We filled 1s and 2s, 2p, 3s, 3p. But after 3p, what is the electron that must be filled? It must be filled in 4s. Okay, and then it's followed by 3d. In this case, you have to say we fill 4s first, okay, 4s, and we put 2 electrons, and then we notice that it's 20, then 4p, and then we add 3d6. But according to the rules, you just notice that we have to keep the number in order. Like you have 1s, the 1s are in together, the 2s must be together, the 3s must be together. So in this case, after writing this, you have to rewrite it again and put 1s2, 2s2, 2p6, 3s2, 3p6. You just reflect these in here, 3d6, and then 4s2. You have to put in your mind, according to the order, you have to fill 4s first. What if I need to fill electrons in strontium, for example? Strontium atom, it contains 38 electrons. We can say we start with 1s2, 2s2, 2p6. We filled 10 electrons. And now let's go to 3s2, 3p6. And now we filled 18 electrons. And now we fill 4s2 and 3d. How many electrons we have to put in D? We filled 10 in here and 10 in here. We need to fill this by 10. We have to say 3d10. And how many electrons left out of 10 in here? We have to fill it by, yeah. And now let's go, what will happen after 3D? Let's go to this and see the electrons, or let's say the outer shell. After 3D, we have to fill 4B. We fill 4P by 6 electrons. We fill P by 6 since we still need more electrons. What is the shell? We have to say, after filling it, we go to 5S. 5S contains 2 electrons. But as we told you, we have to rewrite it again. We don't need to put the 3's together like we need to put the same numbers together. And after that, we have to rewrite it again, and we write 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s2, 4p6, and 5s2. So this is the best way to write the right electronic configuration in this case. Okay, but if I ask you to write this, or let's say to shorthand, how can I shorthand this electronic configuration? Like it sounds, or let's say it looks so long, right? How can I decrease this amount of issues? Like how can I describe it in a smaller way or a little bit more? We can use the noble gas core. Look at the periodic table. We said that noble gas core, and we can see here the noble gases have filled outer shells. The rule says if I need to shorthand the electronic configuration by noble gas, let's stay in our example, which is strontium, and actually strontium in here, we have to jump to the previous period and then go horizontally until we reach to the noble gas here. So we can use the krypton in this case. The krypton contains 36 electrons. And say the krypton contains 36 electrons, which means that we can put all of these and we can write square bracket and we put Kr and then we write 5s2. So what we concluded from this one here, in the noble gas core, we can shorthand the electronic distribution using the noble gases. And the suitable noble gas here is a krypton. And in this case, the 5s indicates to the outer shell electrons or the valence electrons, okay, which are the electrons in the outer shell. And these are for the inner electrons. Okay, so the krypton takes the inner electrons. All of these are filled. You notice that? And here we have the 5s. Okay, let's take another example in more detail about it. But before we go to the example, let's explain something in this example. If I ask you, how can I determine the group number and the period number from this one? But first of all, you have to look at how many electrons are in the fifth shell. We just noticed that we have only subshell, which is 5. We don't have p orbitals or any stuff. And we notice that the s contains only 2 electrons. So the number of electrons in the outer shell is only 2. And thus the group number is 2. Okay? Since the electrons in the outer shell are equal to the group number, then they have 2. Okay? And the valence electrons are 2, by the way. Let's go to the period number. The period number is equal to the number of shells. You just notice that your element is in period 5, and that's why it has 5 shells, and that says 5. Let's go to chloreol. Contains 17 electrons. We can put them like this way. 1s2, 2s2, 2p6, and then 3s2, 3p5. Okay. First of all, this is the electronic distribution. We have 1s, which is shell number 1, 2s, 2p. These are in the second shell, and these are in the third shell. So from this configuration, we can say the period number is equal to the last number here, which is 3. Okay. And the group number, which is the number of electrons in the outer shell, the number of electrons in the last shell. You just notice that the last shell is a 3, right? This is a 3. How many electrons we have in 3 shell? 3. We have 5 electrons and 2. 5 plus 2 equals 7. Then the group number is 7. Okay. What is the block of this element? The block of this element, you have to look at the last subshell occupied, which is P. The last shell is occupied is P, and that's why it's in a block, P block. Okay. How can I write this in noble gas? If I need to shorthand that noble gas core, how can I write it? I look at the chlorine here and just jump to the previous period and just look at the noble gas in here, which is 9, and it actually contains 10 electrons. These are the inner shells. The inner shells are replaced by the noble gas, which is Ne, and then we write after the noble gas the outer shell electrons, 3s2, 3p5. So this is the solution in this case. Okay, but suppose that you don't have this, you don't write the electronic configuration. How can I do it in the noble gas without doing that? Let's say phosphorus. Okay, what is the block of phosphorus? The block of phosphorus is P. Put in your mind. The periodic table here is divided into 3 sections or 4 sections. The section group number 1 and 2 are for s orbital. The middle part in the periodic table is for d orbital. The one below here are for f orbital, and the rest are for p orbital. And you have to put this in your mind well. How can I write P, okay, in terms of noble gas without writing the electronic configuration? First of all, look at P. You say P is in group. You notice that this is group 1, 2, 3, 4, 5. Then it's in a group 5. Very nice. This is in a group 5. What is the period number of P? You have to say 1, 2, 3. Then it's in period 3. Okay, these are the 2 informations which are really nice. So phosphorus is in a group 5 and period 3. How can I translate this? Since we say period 3, it will start with the 3s and 3p because it's in p block. It's in p block, okay, and that's why in period 3 we have to start with the 3s and the 3p. All right, and then we have 2s and 2p. It says that the group number is 5, which means that we have to distribute the 5 on s and p. Since s contains 2 electrons, then the rest is a 3. So this is the outer shell electrons. We write them as they are, 3s2, 3p3, and then we write the noble gas. What is the noble gas here? We have to look at P, which is phosphorus, and then jump to the previous class, previous period, and then choose Ne. So this is the best way of writing that. I'm ready. There's no need to write the whole electronic configuration in this case.